All right, I think we should start. So today we have Alessandra Silvestri. Alessandra is a professor at the Lorentz Institute in Leiden. She is a Italian cosmologist, and I'm very happy to, this is the second Italian cosmologist that I present this year, and both great. So Alessandra did her studies in Trieste, and then she did her PhD in Syracuse. She was a postdoc for many years at MIT, and then in CISA, and then she moved to Leiden. And today she's going to talk about unveiling dark energy from the large-scale structure, the theoretical side of the challenge. So thank you very much.
Let's see. Yeah, sorry, I moved with the wrong side. Okay, so thank you very much for having me here. It's really exciting. I've never been at IAPE, so it's really great. And let me take this opportunity to tell a little bit about the way we are trying to approach how to test gravity and how to understand what the physics of dark energy should be by using large-scale structure. So it's very related to what we do for Euclid in the theory working group, and in general with experiments, missions such as Euclid in mind. So keeping in mind that we'll have a lot of wonderful data about large-scale structure. And I like to start with a picture from Leiden. So in Leiden, I'm not sure if in the Netherlands in general, but in Leiden they have this thing that they like to write things on the walls. So you find a lot of poetry, both on the external walls and internal walls of the houses. And but then in the physics department they thought, well, then we should really also start writing formulas of all the things that somehow are connected to Leiden. So you can find Lorentz contraction on a wall close to where the train passes. So as you go on the train, you see how things contract. And then, you know, Einstein has a link to Leiden. He used to be a visiting professor there and spent a lot of time interacting with Ehrenfest and other people. And so they thought to write also Einstein equation in there with a nice painting. So, well, the idea is general relativity provided us with the mathematical framework that we needed to really study the universe from a scientific point of view. So that's, if you want, when physical cosmology was born. And then you fast forward a century, and observational cosmology has been incredibly successful. It has provided us, through many, many observations, with a standard model of cosmology, with a deep understanding of the universe, how it evolved, and how it came to be what we observe around us today. And so all these different observations, ranging from cosmic microwave background, galaxy rotation curves, Lansing, etc., have come together to give us what we call the standard model of cosmology. It's a wonderful success, but an exercise that has also left us with a quite dark universe. Because in this, and sorry for the colors, but you see that if we take the equations of general relativity, the equation that I showed before, Einstein equation, and we apply to all these observations, we need to put together with ordinary matter, which makes up only 5% of the current energy budget in the universe, two other dark components. Dark matter, which is what we need to sustain the clustering, and dark energy, which is what we need to explain the current dynamics of the universe, how it is expanding. So I will focus, for me dark matter is solved. It's some, let me make this first small assumption. And so it's some cold dark matter there, pressureless clustering. It works wonderfully. And let me focus on the other dark part, dark energy. And the main point, of course, is we infer the need for dark energy by applying Einstein's equation to the dynamics of the universe. So we should keep an open mind and consider that maybe we don't need an extra mysterious component, but we can simply think of modifying the laws of gravity. And I will often refer generally to this as dark energy. Sometimes instead I'll talk about dynamical dark energy, meaning I really introduce some extra component in the energy budget, and modify gravity by meaning that I try to modify the laws of gravity. Then, of course, as I will discuss, sometimes this distinction is not so clean. This is a plot that I borrowed from a paper by these guys here, Marco Raveri, who was my PhD student, and Matteo Martinelli is currently a senior postdoc in Leiden, now moving to a junior leader position in Madrid, and Gombo, I don't remember the first name of the last author, Wang. Anyhow, so they brought this cosmic fish, which is a code to make Fisher matrices and for a lot of different cosmological data. And it interfaces well with other codes that we have to study modify gravity, and I mean, whatever you have beyond the lambda CDM, so beyond the cosmological constant, to try to explain cosmic acceleration or gravity on the large scales. So it's a very busy plot, and where they have used some advanced statistics to look at the information gain in cosmology. And I really want to, I really would like you to focus on the general trend. So different colors are different beyond lambda CDM models. And then the details are not so important. Some of these are Rojava-Lifshitz gravity, some of these are massive neutrinos, etc. But somehow you're doing something that is beyond the standard model of cosmology. And the idea that I want to convey out of this busy plot, where here on the vertical axis you have sort of how much information you gain as your missions come to life for each of these models. And so the point is that for a long time we have learned a lot about the standard model of cosmology. We have now measured beautifully the parameters of that model, but we are now here waiting for this wonderful array of data, and that is really sort of opening our ability to measure more, to start discerning about alternatives to the standard model of cosmology. So the idea is we would really like to exploit that. And let me be a bit more precise. There's many missions, but most of what I will be talking about is related to scalar perturbations, which are the one relevant for large-scale structure. So we have the homogeneous and isotropic universe, and then on top of that we'd look at small perturbations, and I will focus only, of course, the metric. A tensor comes with scalar, vector, and tensor perturbations, but the ones that really couple to matter and are relevant for clustering are the scalar ones, so are the only one that I'm including here. So besides the scale factor described in my expansion history, I have two potentials, two perturbations to the metric, scalar quantities, which are function of time and scale. And you can very schematically think of the perturbation to the time component, since it's the one that entered geodesics of non-relativistic particles, to be the one that you really probe when you go and look at the clustering rate at peculiar velocities and things like that. And instead, the combination phi plus psi, the wave potential, is the one that entered geodesics of relativistic particles. So you should think of it as the object that you probe when you look at weak Lansing or the integrated Saxoff effect on the cosmic microwave background. Now, I'll get to this, but you know that once shear from neutrinos is negligible, these two things are more or less the same. Yeah, so this is there to say weak Lansing. There's many ways we can pick it up. We have cosmic shear, so we have deviation, distortion of of the images of background galaxies from all the large-scale structure that sits in between us and these background galaxies. We can do galaxy-galaxy lensing also and cosmic shear, but you can pick it up, and it has been wonderfully measured by Planck, right? You can pick it up on the high L tails of the cosmic microwave background. Now, let me briefly, it's probably really obvious for most of you, but since I think it's a broad audience, let me briefly, with one slide, review what we know about the standard model of cosmology for what matters, what regards large-scale structure. So if you do the exercise of studying linear cosmological perturbations, focusing on the scalar modes, in lambda CDM, so when you base yourself on Einstein equation, you can have the cosmological constant, it doesn't matter, it doesn't cluster. So, yeah, I should have put it there explicitly because I'm saying acceleration is sourced by the cosmological constant. So imagine here that you have lambda multiplying the metric in that equation. And then if you go beyond the background expansion, you really, at late times, you can focus only on cold dark matter, which is pressureless, and isotropic stresses become negligible, pressure as well. So all you focus on is the density contrast of cold dark matter. And if you do the exercise of studying what Einstein equation, linear Einstein equation tells you for scalar perturbations, you find that it's a pretty simple picture. So besides the fact that the expansion history at late times is governed by the cosmological constant, so W is equal to -1, since neutrinos, the shear of neutrinos is now negligible, the two metric potentials are really the same. And not only, they're not really true dynamical degrees of freedom, and you can see it in Fourier space, for instance. The equation, a combination of Einstein equation reduces to an algebraic one. This is density contrast, sorry, it's similar to this. I'm just writing it in comoving. Just think of this as delta rho. And it's a very simple equation. It's Poisson equation in Fourier space. It's algebraic. So you don't have much to solve. Once you have solved for the expansion history and you know how H of A behaves, then you know also everything else. You know how your dark matter cluster, the rate at which it clusters, it's scale independent, the same for each K once it enters the horizon. So that's one very important characteristic to keep in mind. Phi equals psi, so if you want weak Lansing and galaxy clustering, probe the same quantity. And there is a consistency relation between the expansion history and the rate of growth. Why am I highlighting these three things? Because we have seen, studying modified gravity, for instance, that all these things typically break as soon as you go beyond lambda CDM. And you start having a scale dependence in your growth rate. Importantly, relativistic and non-relativistic probes respond to different things. And that's sort of, if you want, what's behind the idea of combining, for instance, like in Euclid, galaxy clustering and weak Lansing. And also this consistency relation is broken. You have a more complicated growth rate. So that's behind this so-called, what I like to call phenomenological framework to describe modified gravity or dark energy, whatever is beyond lambda on cosmological scales. It really was born out of studying things such as F over gravity, DGP, and many other models, or coupled dark energy, etc., and studying what happens with large-scale structure. And then we came up, I mean, it's a broad we, with this parametrization. So it turns out that you can sort of replicate what you do at the background level, where you put your ignorance in the equation of state. You say if it's not a cosmological constant, W equal -1, it will be something else, it will depend on time, and you try to measure it, right? Some supernova, baryoacoustic oscillation, etc. You can replicate the exercise and forget about theory and say, well, I've seen that as soon as I modify my equations, what happens is that the potentials are not anymore the same, and also the clustering becomes more complicated. It depends on time, but I don't care about the details. I put all my ignorance Oh, I thought you had a question. I put all my ignorance into these two functions. And if you restrict yourself to the linear regimes and scalar perturbation, that's all you need. Two functions of time and scale. It's a very blind approach, but it's what maximizes your use of data. You can throw whatever you measure into something for mu, sigma, and w. So it has become a very popular approach. There is a code known as MG-CAMB, a modification of the Einstein-Boltzmann-Solver CAMB for modified growth that lets you choose whatever mu and sigma and let you fit it to data. And of course, you have to make a choice. So it's a very nice, broad framework where you say, OK, whatever. But then when you face data, you have to make a choice, which is typically what you do here. You choose CPL, W0, WA, a sort of expansion in the scale factor. And many other choices have been made for mu and sigma. Let me just, if mu and sigma don't look so familiar to you, you might have already encountered them under different names. As it happens often in cosmology, there's no agreement on symbols. So mu sigma, you might have encountered G matter and G light, and the point is that by the way we have defined them, they sort of rescale the Newton constant, entering in geodesics for matter and geodesics for light. Or other alternative letters, eta, which is used in Planck, and oh, sorry, gamma, I haven't defined it. It's a combination of these two, and it's really the ratio of phi over psi, the two potentials. Sometimes it's indicated with eta and whatever. I mean, this is just nomenclature. So now this is what Planck, I think this picture is from Planck 2015, but I think it didn't change much with Planck 2018. And this is what we know, for instance, from latest measurements by Planck about W0, WA. And here, of course, you know, it's lambda CD. If it's the cosmic acceleration is sourced by lambda, -1, 0, you expect for these two functions. And this is what Planck gives you. Colors here indicate H0. Sorry, I removed the legend because I didn't really want to focus on that, but just on the contours. And then some forecast for Euclid tell us that Euclid combined with the aid of Planck, of what we know from Planck, will really shrink these contours. We don't know where it will really sit. This is just around the fiducial. Who knows? It could sit somewhere else. But the point is that it will really shrink this area, so it will significantly improve our sensitivity to these parameters. So it starts being important to make sure that we explore regions of this plane that are physically allowed. And also that we are ready to make, once we have any significant, such an impressive measurement, for instance, of W0 and WA, and if it doesn't, which is maybe unlikely, but if it doesn't happen to sit in -1 and 0, but happens to sit somewhere else, that we are ready to understand what that somewhere else is. And similarly, Euclid promises to be very good also for measuring mu and sigma. So this is a forecast done by Santiago Casas and collaborators, where it shows, of course, the way these functions are built, it's trying to keep it in mind a sort of orthogonality. I mean, the fact that galaxy clustering, just by how I have defined mu, is very sensitive to mu, and weak lensing is very sensitive to sigma. It's just by construction. And then if you combine that and also with Planck, then you will really have % or 10% level accuracy on measurement of this function. So it is getting really exciting. And let me detour a little bit with 2 slides about with gravitational waves. So as Stephen Hawking said, now we were straining our eyes, now it's time to strain our ears. So we are not only seeing stuff, we are starting to hear stuff. And that's once after LIGO has measured gravitational waves. And in particular, there was this huge impact of the multi-messenger measurement of the binary neutron star merger, which was seen not only in gravitational waves by LIGO, Virgo, but also by an array of telescopes in the electromagnetic, the electromagnetic counterpart was picked up. And that was really important because it allowed to sort of localize with a much higher accuracy the source of this signal. And now I'm dropping scalars and I'm looking at tensors. So think of this as the tensorial perturbation, the true tensor, transfer tracer perturbation to your metric. And that's, once it's emitted, that's how it propagates on a cosmological background. And you know, there is this quantity here, which is the speed with which this wave propagates, and this wonderful multi-messenger measurement allowed to put a very strong upper bound, really significantly improve on this bound by many, many orders of magnitude, and basically telling us that, at least at the redshift where this measurement was done at the frequencies, so the energy scales characteristic of this event, the speed of tensor should be equal to the speed of light, which is okay, really nice, wonderful. And one would say, were we really thinking it should be something different? And then people realized that, well, I'll get to that, but many of the models that we were playing with to explain cosmic acceleration happen to be modifying also the speed of tensors. So there was quite a big shake in the gravitational, in the modified gravity community, and I'll get to that. So, but I want to use it to make 2 points. So the first point is we are expecting this wonderful array of data, Euclid and many other missions, but are we ready to make the jump and not only measure W0, WA, mu0, mu-A, whatever, but understand the physics that is behind that, if it's not lambda? And can we exploit complementary information coming from regimes that we thought were completely independent from us, but somehow, because eventually you have a theory, so you have an action, and you treat together scalar, tensor, and whatever, somehow place some constraints on what you can do on large cosmological scales to explain cosmic acceleration. Now, since cosmic acceleration was discovered, theoretical cosmologists have been very active in trying to come up with explanations. And they went, I like to call this Le Verrier approach and this Einstein approach, because it's sort of thinking that you have a dark planet there that you haven't yet seen, but is modifying the orbits of your planet. So you have something there, some dynamical component, the dark energy component that we haven't really picked up yet, but we see its effects. Or really, there's no other planet out there, but you're using the Brown laws of gravity, which is what Einstein did for Mercury instead, right? So very schematically, of course, it's not so black and white, and there's also an in-between sort of area, which goes in the back reaction and the landscape scenarios, etc. But all I want to get out of this picture is that it is a mess, and it's quite hopeless. I mean, everybody has his own preferred model, but really none of these are standing out. From the theoretical point of view in particular, there's no front runner. Some models have nicer properties because maybe they are able, for instance, the gravitation was an attempt, do I have it here? Yes. The gravitation was an attempt at not only explaining cosmic acceleration with some dynamical degrees of freedom, but also solving the cosmological constant, the vacuum energy problem. Explaining why, if you want to source your cosmic acceleration with something that is not vacuum energy, and you don't need to fine-tune then your vacuum energy such that it sources acceleration, you still need to put it to 0, because you expect otherwise a huge contribution from there. Many of these models try to explain cosmic acceleration, completely forgetting about the problem of vacuum energy. So you might have some theoretical reasons for saying, well, the gravitation is nicer than the others, but really it's a very intricate labyrinth. And I mean, that's something that if you give it to people that will provide the data, for instance, for Euclid, they really hate you, because that's not a proper framework to do an efficient and meaningful test of what our theory of gravity could be there. So it turns out that most of the models that were in that branch can be, at least as long as you worry about the phenomenology of linear perturbations, can be, can be written, represented well by these so-called generalized Galileans, and where you have an extra scalar degree of freedom. Sometimes it's an actual degree of freedom that you introduce, like dark energy. Sometimes it's just, I don't know, the longitudinal mode of a massive gravity, or something coming from the tension of your extra-dimensional, of your brain in the extra-dimensional model of gravity, whatever. At the end of the day, at the energy that matters for cosmological observables, most of your models fit well in this description of having, besides a massless graviton, an additional scalar degree of freedom, which with second-order equations of motion. That's all this Lagrangian is saying. It's a very complicated Lagrangian that makes sure that the resulting equation of motion are not higher than second order. Now, it's known as generalized Galilean, but it was written already in a more geometrical language by Hordesky back in the 70s. He was a student of Lovelock. So he tried to, Lovelock studied the most general theory of gravity for your massless graviton in 4 dimensions and more dimensions. And then he asked his PhD student to do it for your graviton plus a scalar field. And he did a wonderful exercise, but then left the field and became a painter. He's a successful painter, actually. We have just contacted him because we were hoping to buy a painting from him. He has this, because then he left the field, right? And then some years ago, suddenly he realizes that his paper about this Lagrangian has 1,000 citations. And so he comes back and he starts writing papers, and he has made also a painting that says my favorite scalar tensor action. And he details not only the action, but on the frame of the painting, he details how he constructed it. So I'm trying to convince people in Leiden that it's a worth investment. But anyhow, so just to say, it was already there many, many years ago. And then it became again, we sort of went back to it from a different route, which was starting from massive gravity. But in here, what you have is that the freedom to move in on that tree of models goes into these functions, function of the scalar field and its kinetic term. Maybe we have made progress, we have an action, we are unifying all models, but it's still difficult if you face data to try to learn something about this function of phi and x. So let me get to what we think is a good intermediate way to make to keep close to theory, but still make things feasible data-wise, which is effective field theory. It goes back to Weinberg for inflation, and then Creminelli, Vernizzi, and other people took the same formalism and applied it to quintessence, and then eventually, a few years ago, in particular, here, Giulia Gubitosi, Filippo Vernizzi, and some other people elsewhere have applied this formalism to dark energy, or if you want, cosmological, linear cosmological perturbation. So it looks awful, but it's a way of organizing your ignorance about what dark energy or your theory of gravity could be on the cosmological scales, and your ignorance now goes into these functions of time. And the way, I'll try to say a bit about this, but I don't really want to go too much into the technical aspects, because I really want to just use it as a very nice unifying action. And okay, you will tell me, yes, thank you, you're moving dust from under one carpet to the other. You still have 5 unknown functions of time, but I will try to argue why we think this action is very powerful. And the main thing is that it is an action. So before, the mu and sigma was a very phenomenological approach. I was putting my ignorance in parametrizing how phi, psi, and delta rho were related. I was very far from theory. Here I'm parametrizing my ignorance at the level of the action, and there are sort of several positive aspects, but the two I want to highlight now, before I explain it more, is that it's not specific to scalar, because out of this action I can study also tensor perturbations. And since it is an action, I can study the stability of my theory. I can study whether this theory makes sense from a physical point of view, whatever choice I make for these functions in red, which in other words says you cannot have any value for this function. Now, let me just try to say in few words how it's built. So that it's a sort of, you look at your scalar field as being related to the breaking of your time diffeomorphism invariance. Because you have something dynamical that sources your acceleration. You don't have a cosmological constant. And since you're breaking that time diffeomorphism invariance with a sort of spontaneous breaking mechanism, you free up this sort of gauge mode, Goldstone mode, which is here represented by having terms in your action which explicitly break time, the invariance under time transformation of your time coordinate, but still obeys spatial diffeomorphism invariance. In a very simple words, what you're writing down is an action that is quadratic in perturbations, because you want to stop at linear level, and for a theory where besides your massless graviton, you have also an additional scalar degree of freedom. Why it looks so hopeful? Why don't you see phi and etc.? It's because you have absorbed that scalar degree of freedom into your metric, which in other words says you have adjusted your slicing and your constant time hypersurfaces in such a way to coincide with uniform field hypersurfaces. This is very technical, but it's just a trick to absorb your scalar field and make it reappear, like you do with the X mechanism, right? Make it reappear in the metric. So now your action can contain explicit dependence on time, which you usually don't have, because you need independence under 4 diffeomorphism, and can contain such things with loose time indices. And that's in here really, this represents what you typically call delta phi. It's related to the kinetic term of your scalar field.
What is this time?
Sorry?
What is this time? Which time do you consider? A founding time? Or?
In here I think it's cosmic time. You can do it in conformal or cosmic, whatever, yes. You have to be very careful once you choose the time in which you do it. Yeah, yeah. And maybe I'll skip this. If you want, you can ask me more and we get back to it, because I think otherwise I spend too much time on details that are not so relevant. But this is just to give a picture of how you construct and what all those quantities that enter that I didn't really explain, like the extrinsic curvature, etc., appear there, and why do they appear there. But so let's trust the people that built this action, and now our ignorance has moved into these 5 functions of time. And I've been very slow, okay. So 5 functions of time, and the nice thing is that not only you can treat now everything scalar, tensor, etc., but you have a mapping. Any of the theory models that I show in that tree can really be phrased exactly into this action. You have a mapping. Whatever model you choose, you will know what this function should be like. So it's a sort of unifying language. And you might have not seen that action, but you might have heard about the alpha functions, alpha m, alpha k, alpha t, and alpha b. They are exactly equivalent. It's again a way of parametrizing at the level of the action what dark energy could be, but it tries to keep it closer while it's still in action, so we are very close to theory. It tries to organize the objects in this action in such a way that each of these functions has a clear link with observables. It's not, of course, a clean-cut thing, but alpha t is very important to highlight because it's really the one that as soon as it's not zero, not only you're modifying your large-scale structure, but you're modifying also the speed of your tensors. Also this one here, which is related to having a conformal coupling, modifies the friction term in your tensors. So they are very equivalent as approaches. I use the first one that I showed just because we have a code built on that one, but also because I like that it is very diagonal in the sense that the more operators you turn on, the more of those red functions you take them to be different from zero, the more complicated your theory becomes. So you can go very gradually from lambda to more complicated scenarios. And now let me touch on stability. We want you to live in a stable universe. We don't want things to just go nuts as soon as you perturb them slightly. And that can be done very technically. Since you have that action, you can really try to expand. It was written in terms of geometrical quantities, right? Perturbation to the metric, to the curvature. But then you can break it up and expand in the actual the perturbations of your metric that I'm calling here psi and h. This is the tensorial one, and this is the scalar one. If we were in the standard case, there wouldn't be any dynamical scalar one. We have seen indeed, you have algebraic equations, right? You don't have any propagating scalar degree of freedom in GR, in the standard case for GR. But now you are modifying your theory, so you have a propagating. You remove all the spurious degrees of freedom, you're left with these two, a propagating scalar and the propagating tensor. And then you can impose some very popular conditions of stability. Things that basically, in simple words, will make your perturbations grow exponentially if they are of the wrong sign. Some conditions, the one related to the positivity of this term that multiplies the kinetic part of your scalar field is known as the ghost condition. No ghost, you need this to be positive. There is a gradient condition related to the positivity of the term in here, and there could be more conditions. It's a very tricky exercise. Also because these are effective field theories, so in principle there will be a UV completion. So in principle some, not all, but some of, depending on the type of instabilities, they could be cured by having a UV completion. But let me show with an example how we want to use these stability conditions. And this takes me to the very simple example of quintessence. And in the next slide, I relate this to the W0 WA plane. So you know the phantom divide you might have heard that says that with simple quintessence you cannot cross the boundary of W equation of state being -1. You cannot go below that. And that's, you can see it here. So take an action for a scalar degree of freedom, phi, its kinetic term, and then think that your density here is only a linear function of your kinetic term. So it's really the simple quintessence you are used to. Now look at perturbations of your scalar field around the background, and I'm absorbing it again in the metric, but never mind. So think of pi as delta phi. Now, if this P is this typical one of quintessence, so linear in X, then this is what your action will look at quadratic level. And the no-ghost condition that is having a positive coefficient for your kinetic term translate in having W being bigger than -1. Okay, you tell me, well, fine, but I could have a more complicated action. I could have other operators in there that could come, for instance, from the fact that my P is not so simple. It might be a quadratic function of X. Yes, you could. Then that will give you an extra term here. So yes, you cure, I have this issue. Yes, so now the no-ghost condition becomes different from 1 plus W bigger than 0. So you could cross the phantom divide without developing a ghost, so without developing an instability. But You have to keep in mind that you can do that by adding a term here, which will have an impact on your large-scale structure. So you're protecting yourself from a ghost, fine, but if you study, for instance, the plane of W0, WA, and you allow for region that go below -1, you have to tell me how you went to -1. Did you go to -1 having an extra operator? Then you should have taken that into account when you do cosmic microwave background and weak Lansing, because they will modify your clustering. Or you might do that for maybe having having a multi-field scenario. Okay, so I should really hurry up, but I wanted to make this point clear because it's a bit confusing how we try to use these stability conditions. So here is the example. These are some results from kids, the weak Lansing survey, where they gave constraints on W0, WA, and we were playing the exercise of what could be this, and it happens to be in the phantom, below the phantom line, but of course they put the constraint using the PPF formalism in CAMB, which allows you to go to -1 without worrying too much about which theory will take you there, but you don't modify the clustering because you're still assuming quintessence, maybe multi-field. So fine, you could go there, but you have to remember that a stable Hordensky model will probably not take you there, because to take you there, it needs to have extra operators that will modify your clustering. So it's very important to remember which regions of this parametrized plane can be explored. And then we try to extend this exercise to large-scale structure. So let me briefly tell you what we are trying to do. We are trying to build what we call theoretical priors. So using that, we still think that W, mu, and sigma are the best way for us to make contact with data. What we want to do is try to guide the data in the proper regions for mu, sigma, and W. So we want to do a sort of cleaning up of the parameters, of the phenomenological parameter space, and we do the cleaning up using effective field theory. So we use that action in terms of those unknown functions, and then we try to expand them, this function, in many different ways, as function of the scale factor, for instance, and sort of Monte Carlo sample this space, somehow creating many, many models. We do it for more than 10 to the 6 models, and we subject them to conditions of stability. So for each of these models, we study whether they would develop or not instabilities. If they would develop instabilities, we throw them away. And then we keep those, and sometimes this cut is huge. It cuts like 100 or more 1,000 models out of the original set. So we are left with something like this, and then we use our code, which is yet another modification of CAMB, which implements effective field theory, to predict what cosmic microwave background, weak Lansing, clustering, whatever will be for these viable models. Of course, this is not what we want. We can plot spectra, but what we really want is something like this. So again, a very busy plot, sorry. Let me guide you through it. Here we are looking, so in simple bore, we are really projecting what the theory allows me to do from this EFT approach into the phenomenology of large-scale structure. Here we are looking at each box is mu and sigma, so here is modifications to weak Lansing. If it's 1, it's the standard behavior, and again, here modifications to clustering. If it's 1, it's the standard behavior. So every origin is lambda CDM. And we are looking at it at different times. So as you move from left to right, you go towards today, and at different scales. If you move from the bottom to the top, you go from very small to large scales. Now, don't worry too much about red and black. It's a difference between an exact evolution, full dynamics of perturbation, and the quasi-static, but I didn't get into that, so just focus on the red, but I mean, here they overlap perfectly. So this is just telling you, be careful with quasi-static if you're familiar with quasi-static, otherwise don't bother about what I'm saying on large scales. On small scales, that's so out of this whole plane, Hordesky, generalized Galilean, most of the models that I show in the original tree, viable. So after you impose stability, won't take you much around the plane, but will really align on this sort of diagonal. So we sort of know what to expect for the phenomenology. And most of the cleaning is done by asking the theory to be stable. Some cleaning is done also by additionally imposing what we know from solar system. So now I think I should wrap up. So let me skip a couple of slides, which are not so important. And let me go back to gravitational waves. So the cleaning I show you in there was based only on stability conditions and on some constraints that we know from local tests of gravity. There is this gravitational waves, right? I made a point about wanting to use also this complementary information from tensors. And before I showed how tensor propagates in the standard case, now if I have that action, it modifies not only how the speed of propagation. Ooh, I'm missing a k-square here, sorry, there should be a k-square. But it modifies also here the friction term. Now it turns out that requiring this to be 0 puts one of my free function in that action to 0. But actually, if you look at it from the point of view of which models survive, it has quite a pretty strong effect. And there's been a whole PRL issue dedicated to that, several papers. There's also some caveats that need to be taken into account because of the energy scales of these effective field theories and the energy scales at which these events has been picked up. So it's not, there's a nice paper by Claudia de Ram pointing that out. Lisa will eventually settle this. Anyhow, let's say that now CT square has to be equal to 1, not only today, but at all redshifts. That has a big impact. And the interesting thing is that it has a clear impact on what phenomenology we can expect for large-scale structure. I don't want to show it in formula, but I want to show it in plot. So again, going back to, I'm picking out just one of the quadrants in that big plot that I had before. Before I had dots, now we made it solid. Anyhow, I told you most of the cleaning was done by stability. You cannot really go here, like for instance in the W0, WA plane, you couldn't go below the phantom divide. You cannot go here because of solar system. I mean, it's not so, this box is schematic, right? It's not such a strong cut, not only, also because of the precision of the measurements. I mean, there's some wiggle room here due to the error of the measurements, right? But then this is, the blue is wherever, what Hordesky is left to give you. And if additionally you ask Hordesky to satisfy speed of sound of tensor to be equal to 1, then it narrows down. And you really have a sort of diagonal where you go back to mu and sigma being the same. Not necessarily 1, but the same. That's the effect. So let me show you. So this is Hordesky with CT square equal 1 today, and what we expect for mu and sigma. This is Hordesky with CT square equal 1 all the times. It really, if you look at here, for instance, it really narrows it down to a diagonal. So that's the way we are trying to use the effective field theory approach. Let me give my 2 cents about this and what I try to convey. So I started with this, sorry, I should have said sigma here, with this phenomenological approach where you put your ignorance into what large-scale structure can do into those 2 functions of time and scale, mu and sigma, or mu and gamma, whatever, which are a generalization at the linear level of W of A. Now that has been very useful in learning how much our data are or will be sensitive to possible deviations from lambda CDM, and in basically just pouring all the data can say, storing all the data can say into these functions. Then we can maybe worry later about what that means from the physical point of view. You can do that. The thing is that you might waste a lot of time into moving in regions of the parameter space for mu and sigma which don't make any sense from the theoretical point of view. So that can be cured with these so-called effective field theory approaches, which start at the level of an action. You don't want to fit that action to data. That's not what you want to do. You have too many unknown functions in there. But you can use it to sample your theory space, to understand what are viable regions, what are not viable regions. And eventually, we think a very powerful way forward is to project whatever you learn into this EFT language into the phenomenological one. And you want still to be quite general and have a very simple interface with data, but you want to clean up that interface, make it more meaningful and more efficient by projecting what EFT tells you for it. So I think I'll stop here, and I just make a point that the way we hope to use these theoretical priors, I show you a lot of projections, like what do they imply for mu and sigma. The way we really want to use them is technically building theoretical covariance matrices to combine them with the data one and eventually sort of try to non-parametrically reconstruct the physics out of all these wonderful observations. And I'll stop here.
Okay, thank you very much, Alessandra. Questions? Yes. Can I start here?
So I have two questions. One is, let's go simple. You applied the Copernican principle to the speed of gravitational waves compared to the speed of light in the end. Mm-hmm. And let me do it also for W, right? So we know that if you assume that W is constant, we've known for 15 years now that W is very close to -1, yeah, within maybe 0.05. Now it's 0.03. And so you might wonder, you really have to have a contrived theory to have W be different from -1 at early times and be -1 today. So I was wondering what you think about that. And my second question is, now that we have this constraint on the gravitational wave speed, what fraction of your cosmic zoo of what you call the theoretical landscape goes away, or do they have so many internal parameters? You mentioned that if you want to fit the action, you have too many free parameters, that they can all get away with it because they have so many free parameters.
Yeah. So I think theories will always be able to get away by any constraint, but yeah, we might not really like the theory that comes out of that. So let me address a little bit the W equal -1. We do know indeed that it's very narrowly constrained around it. The one point that I want to make is that we have to be careful about the way we extract these constraints, because we do fit things such as W0, WA, which do not allow, maybe we are not really picking up a possible true dynamics that would be there. So we are sort of, if we give data W0, WA, then yes, it will prefer and severely constrain it to be -1 and 0. But maybe by doing that, we are losing up, we are integrating, right, also basically on W, right? So we might be blind to something, some dynamics that is in there. And the similar thing with mu and sigma. So the exercise we are doing is really trying to, of course, the first thing you want to do is to have a meaningful test of lambda CDM, but to make it meaningful. So one reason of exploring all this zoo is also so that if I really have to surrender to -1 and 0, I'm sure from the statistical point of view, I've done it in a meaningful way. I've explored meaningfully the alternatives. Now, CT square equal 1, yes, it's similar. Again, one could argue that it has been measured at very low redshift, but then it's a fine-tuning problem, right? If you want to just say, no, it's 1 today, and it's whatever, I have total freedom. So again, it makes your model really unpleasant. If you assume it's 1 all the way, it has quite a drastic cut out of that tree of models. In particular, it cuts away most of the nice self-accelerating models. And models that were truly giving you the acceleration not from a sort of cosmological constant. And it cuts out all models that basically on nonlinear scales are characterized by the Weinstein mechanism. So all models that have a non-trivial kinetic term. Because whenever in your action you have a non-trivial kinetic term, your alpha t, or your correction to the CT square, will be non-zero. So having that be zero means that you throw away non-trivial kinetic terms, so you're basically back to very like generalized Brans-Dicke model that have a simple kinetic term, but can non-conformally couple to gravity. Then when they non-minimally. When they non-minimally couple to gravity, they modify also the dispersion term in the propagation of your tensors. And that's something that eventually we will be able to measure as well, because it basically, having that dispersion term being different from the standard, sort of rescales the luminosity distance that you infer for your source from gravitational wave measurements. So by comparing the luminosity distance that you infer with the electromagnetic counterpart and the one that you infer from the waveform, you can place a very nice constraint on the conformal coupling. So eventually that will do also a lot of cleaning. Yeah.
It was more or less the same. My question was more or less the same one. I mean, if you're going to bet, and if the Euclid showed that W was not -1, and you didn't mention anything because, of course, I'm an observer, right? So all of we've been hearing a lot about tension between Cepheids and Planck and so on. So you make your comment if perhaps Euclid was launched tomorrow and it showed that W was -1. What was the first thing that you would test? That's all.
Sorry, what's the last thing?
If Euclid was launched tomorrow and W was not -1, then what's the first thing you would test?
In terms of models? No, well, yeah. I'm not sure out of that three, I'm not sure at what I would really test. The next thing I would do is look at what mu and sigma, so what the clustering does, because that would tell me also a lot of useful information about the model. And then it's a still complicated reconstruction. Yeah.
Hi.
Hi.
So, in the equation of the propagation of gravitational wave equation you showed,
yeah,
there's a frictional term, the second one.
Here?
So yeah, that one. So do you consider the effect of that in your constraint, in your contours for the CT equal to 1?
No.
No.
We only look at here, again, there's a k-square missing,
yeah,
so we only look at the effect of putting M3 to 0. We didn't look at this. And yeah, so that the thing I mentioned about that is that you could eventually constrain it from this luminosity distance. The other way people phrase that is be careful when you measure H0 from standard sirens, because you might be thrown off by having that really being non-zero. So it's, yeah, but no, we haven't looked at that. Actually, I don't think currently, I mean, sorry, maybe what I should say is that this is the conformal coupling, right? It's when your scalar field is non-minimally coupled to gravity. And as soon as you have that, you have this additional force which is mediated that you need to screen on small scales, because we have tested GR wonderfully on small scales. And for that screening to be efficient, you have very stringent bound of what omega can be. Other bounds come also from BBN, because this omega would basically give you a running of your coupling constants and masses. Yeah. So there are several constraints that we have already on what omega can be, and I put it there. That's when yeah, solar system, that's exactly what I mean. And I think there's no, right now, gravitational waves are not at all competitive with those constraints. But eventually, yeah, maybe.
So, and the plot for the mu and sigma you have shown?
Yeah.
As a function of A and A, redshift, and K?
Yes.
There, how much degeneracy you have with, say, sigma 8 and neutrino?
Degeneracy?
Yeah.
Yeah, so with neutrinos, with massive neutrinos, it's quite severe, because it's a similar, in scale, it's a very similar effect. And actually, it can compensate. because typically what these theories do on smaller scales, they enhance your clustering, which is the opposite of the free streaming of neutrinos. So yeah, it's a degeneracy that you definitely need to take into account. In terms of sigma 8, yes, you do expect also your F sigma 8, for instance, to inherit some of this scale dependence. Bear in mind that it's very unlikely that we will really pick up that scale dependence. It's related to the mass of your scalar degree of freedom. And there might be argument towards having it very large because you want a light degrees of freedom sourcing acceleration, or you need it to be instead not so large because you need your screening to be efficient. So most of the times the models sit on one or the other extreme, close to nonlinear or very large, and in between you don't see your scale. And it depends also on the range of scale that you will pick up. So it's very unlikely that with one experiment you really see this transition in scale. Where you need to be careful is when you combine things such as weak Lansing and cosmic microwave background, they probe very different scales. If you see discrepancy, for instance, yeah, in sigma 8, the way you infer it from weak Lansing and cosmic microwave background, it could be due to the fact that in between you had a transition and these functions change, but yeah, very ideal. You had a question? No.
I have one question and one comment. My question is that you mentioned when you use the effective field theory,
yes,
it somehow simplify the model.
It organizes, let's say,
yes,
the model. Yeah.
Hordensky model, which is more complicated. However, then you are, as I mentioned earlier, you depend, your analyses depend on which time you are using. Then this can be, can affect everything, actually. Mm-hmm. And I think that, I don't know if...
which time, you mean in building that...
exactly, in the formula, because in this formulation, at least, you are breaking the diffeomorphism with respect to time. Therefore, everything will depend on how you define your model. Therefore, this is a bit dangerous.
You have to be really consistent. So you have to make sure. So if I can choose cosmic time or I can choose conformal time, then since I'm absorbing this degree of freedom into perturbations of the metric, so basically into a perturbed time coordinate, yes, I have to be very careful the way I translate the perturbation of my scalar field, or vice versa, the perturbation of my metric in the perturbation of the scalar field. But if you are consistent all the way through, eventually once you face data, there shouldn't be any spurious dependence.
And my comment is something very general, because all these modified gravity that, for instance, Hordensky that you have shown depends on a large number of derivatives. Mm-hmm. And okay, if you want to, for instance, find deviation from Einstein theory at smaller scale, for instance, scale of black holes. Such models are good, but for explaining dark energy, you have we know that dark energy is very, very isotropic. Therefore, it means that in any case, any derivative term is very, 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 very small, if even exists at all. Therefore, the failing of the model is roughly guaranteed without even thinking about it.
You can, there's, so those functions, I'm not sure I'm interpreting correctly what you're saying, but those functions in which I'm now putting my ignorance about what dark energy could do, I do know, I do have some constraints on how big they should be, and also on their time dependence in order for this model to be any reasonable. So yes, and yeah, but.
So one last question.
When you apply the test on the speed of gravitational waves, I think that there are still some interesting theories which remain. For instance, the cubic Galilean, which is still allowed and may give you a cosmic acceleration. Mm-hmm. But I have a question. So it's more complicated than generalized Jordan-Bronsdicke theory, I think. But okay. But for the Ordensky, in this plot, do you include also the beyond Ordensky theories and beyond Ordensky theories known as Dost theories? Okay. And I'd like also to know why in the Ordensky, when you apply the gravitational wave speed test, finally the effect on the large-scale structure is about the same as the effect of the lens on the weak lensing. That is, mu is equal to sigma. Why physically?
Okay, so yeah, we haven't, for the first part, yes, I should have mentioned indeed that there's more beyond Ordensky. And actually one of the papers of Ordensky was concluding when it was like, nobody goes beyond Ordensky without me. So that's when he came back and started to write papers. But yeah, so there are these DH hosts, which are ways of still keeping your equations of motion second order, but having more than the terms that I have included. We haven't studied them. We are studying, but I haven't shown any results.
No, the equations are not second order, beyond Ordensky.
The original knows, but the equation for the true propagating degrees of freedom are still second order, yes. So yes, you have higher order operators in terms of the derivatives, yes. So no, that I don't have any results. I don't know what to expect. We had this conjecture that for Ordensky, the speed of sound of tensor being equal to 1 would keep you on this diagonal. I'm not sure if there is maybe the simple way of looking at that is that modifications, if you start from an action, modification to the speed of tensors are very tied to the anisotropic stress that your theory would have. At the end of the day, you're looking at that transverse part of your either metric or energy momentum tensor. So it usually goes hand in hand that if your theory introduces an effective anisotropic stress, which would be mu different from sigma, it will also affect your, it's not the...
Because this is the scalar part.
Yes, but typically if you start from an action, whatever term in your action will contribute a sigma, a shear for the scalar sector is related to the term that will give a speed of sound of tensor different. There is a sort, it doesn't hold, for Ordensky it holds perfectly. There is, as soon as you have non-zero anisotropic stress, you have also alpha t different from 0, and vice versa. For beyond Ordensky, not necessarily. So, but that's what's behind this. You go on the diagonal because you're killing the anisotropic stress that your theory would introduce. Yeah.
One very last.
So, do you have to deal with problems like galaxy bias and late time nonlinearities?
That's the real world, yes.
But you do or you don't for now?
Huh?
You do or you don't? I mean...
Well, I don't right now. Of course, that's something that you have to deal, and also non-linear regime, right? I greatly glossed over that, and there will be a lot of data in there. So eventually, besides bias, we also want to be able to use the data from the non-linear, and all this is linear. So yes, but it's in principle, yes. There's also, yeah, there is a way of approaching the galaxy bias in this. Well, you could make the exercise of keep going up with that action and introducing more terms, but then it becomes really hopeless. You have a lot of free functions. What the current best way to do it is you go a little bit into the quasi-linear, so you do expand this action to some higher order, but then you make a jump and connect that with instead a parameterized description of the screening. Because most of this model, you have a lot of models, but at the end of the day, the way they screen are very few. They go screen by chameleon or Weinstein or camouflage. And so you can parameterize those three. The trick is to understand, depending on which model, which operators you have in your linear action, what type of screening you expect. It's a very tricky exercise. I mean, this is a sort of effective theory. But yeah, we're trying to make progress in there with emulators.
Okay, so let's thank Alessandra again. Thanks a lot.